Hello everyone, welcome to Unacademy. My name is Shreyas. I'm an educator at Unacademy. You can follow me on the Learning app where you can see my new set of courses, also courses by awesome educators. So this is a lesson about analysis of steam cycles. So what are the different parts of a steam power plant and what are the cycles affecting the steam power plant? Let's get to know in this lesson. So please don't forget to rate, review and share the lesson, and don't forget to subscribe us on our YouTube channel, that is the Unacademy Engineering Curriculum. So guys, let's move on with the course or the topic power plant engineering. I've given my introduction already. This is my Unacademy user platform. You can follow me over there. So let's move on with the course, that is the Introduction to Power Plant Engineering Part 1. So what are the target audience for this slide? The target audience for this slide consists of, or this presentation consists of, engineering students, general audience who are interested in thermal engineering topics, people who are interested in mechanical entities, people who are interested in energy resources, and environmental enthusiasts. So what are the learning outcomes from this presentation? Mainly you guys will come to know the basic outline of a steam power plant, what is a Rankine cycle, what are the different outcomes or what are the different works of economizer, evaporator and a superheater, what is a Carnot cycle, and what is mean temperature of heat addition. So let's move on with the lesson, analysis of steam cycles. So let's have a quote before the starting of our lesson. Analysis is the critical starting point of strategic thinking. A psychological quote. Let's move on. So what is a steam power plant? A steam power plant is a device where it continuously converts the energy stored in fossil fuels, that is coal, oil or natural gas, or fissile fuels, that is uranium, thorium or other materials, into shaft work and ultimately into electricity. The working fluid is water, which is sometimes in the liquid phase and sometimes in the vapor phase. You can see if fossil fueled power plant, it is actually a bulk energy converter and it converts fuel to electricity using water as the working medium. Energy released by the burning of fuel is transferred to the water in the boiler to generate steam at a high pressure and temperature, which then expands in the turbine to a low pressure to produce shaft work. The steam leaving the turbine is condensed into water in the condenser, where cooling water from river or sea circulates, carrying away the heat released during condensation. So you can see this is what a steam power plant looks like. The water or the condensated water is then fed back into the boiler by the pump and the cycle goes on repeating itself. The working substance water thus follows the BTCP path, that is boiler, turbine, condenser and the pump path of the cycle interacting externally. Since the fluid is undergoing a cyclic process, there will be no net change in its internal energy over the cycle, and consequently the net energy transferred to the unit mass of the fluid as heat during the cycle must be equal to the net energy transfer as work from the fluid. So you can see here, this is what a flow diagram of a steam power plant looks like. You can see here, this is where the fuel or the air is fed, and you can see the presence of a condenser over here and the turbine over here and the economizer and superheater, which I'll be discussing again in the coming set of slides. So let's move on to Rankine cycle. So what is a Rankine cycle? For each process in the vapor power cycle, it is possible to assume a hypothetical or ideal process which represents the basic intended operation and does not produce any extraneous effect, that is heat loss. For the steam boiler, this would be a reversible constant pressure heating process of water to form steam. For the turbine, the ideal process would be reversible adiabatic expansion of steam. For the condenser, it would be reversible adiabatic expansion. For the pump, it would be a reversible constant pressure heat rejection, and for the turbine, it will be a reversible adiabatic compression of this liquid, which is ending at the initial pressure. And in the Rankine cycle, when all the four processes are ideal, it is called a Rankine cycle. This is also a reversible cycle, and you can see it can be plotted on the cycle as a PV or TS or HS coordinates diagram, which I will be showing in the further slides. And when we apply the SFE equation, that is the steady flow energy equation, to each of the process on the basis of a unit mass fluid and neglecting changes in the kinetic and potential energy, the work and the heat interactions can be evaluated in terms of properties of the fluid. So you can see here I have derived the equation, the formula over here. You can see applying the SFE equation for turbine, for condenser and the pump, we get the Rankine cycle efficiency as follows. That is the turbine work minus pump work into the heat. And by taking the net change, by applying the integration over the 4 and 3 states, you get the following, and the steam rate is given as 1 by the net work done, and the heat rate is given by heat by the turbine work minus the pump work. So let's move on to the internally irreversible Rankine cycle. Internal irreversibility of a Rankine cycle is caused by fluid friction, throttling and mixing. As the flow rates in the steam turbine as well as in the pumps are large and the expansion and compression process are quite rapid, the heat loss per unit mass may be considered negligible. Though the assumption of the adiabatic flow in them is still valid, due to the fluid friction, the expansion and compression process are not reversible and the entropy of the fluid increases. The internal or isentropic efficiency of the turbine is given by H1 minus H2 divided by H1 minus H2S. So continuing, the pumping process, which is being adiabatic and irreversible, also results in an increase in entropy, and the isentropic efficiency of the pump is also given by the pump efficiency, that is H4S minus H3 divided by H4 minus H3. The actual pump work would thus be, H4S minus H3 divided by the pump efficiency. One thus pays a penalty for the irreversibility, that is the turbine produces less work and the pump absorbs more work. The liquid leaving the pump must be at a higher pressure than at the turbine inlet, because due to the pressure drops due to friction in boiler heat exchangers and other things, it results in the bending of the valves and the pipes. The P4, it actually represents the exit pump pressure, and the pressure of the stream drop occurs from P5 to P5 dash, which I will be showing in the TS diagram, and due to this there will be friction in the pipeline and also the entropy decreases from 5 dash to 1 due to the heat loss. So you can see here internally irreversible Rankine cycle. So I was telling 5 dash to 5, all those which I have explained in the previous slides, you can put it over here, and the formulas which I had told, the turbine efficiency, pump efficiency and the work of the pump is actually mentioned over here. So let's move on to the externally irreversible Rankine cycle. It is due to the external irreversibility of the Rankine cycle. It is actually caused due to the temperature differences between the combustion gases and the working fluid on the source side. The products of the combustion or the fuel gases get cooled from A to D, and the working fluid temperature rises from the state 4 to state 1 in the counterflow heat exchangers. The minimum temperature differences between the two fluids are C to 5 and A to 1, and the points where these occur are called as pinch points. Too small a pinch point temperature difference can cause a lower thermal external irreversibility and an increase in surface area, which is resulting in a large expensive steam generator, whereas a large pinch point temperature difference results in a small, inexpensive steam generator but with a reduced plant efficiency due to large thermal irreversibility. The most economical pinch point temperature difference is obtained by optimization, which takes into account the fixed charges, that is based on the capital cost, and the operating costs, which is based on efficiency and hence fuel costs. So you can see here the A to 1 external irreversibility and the 2 to A, which is given by external irreversibility 2. This is 1. So A to 1 is actually pinch point 1, and C to 5, it is actually the pinch point 2. You can see here all those I have mentioned in the TS diagram. So let's move on to economizer, evaporator and superheater. Heat transfer to water in the steam generator takes place in 3 different regions. Water is first heated sensibly in the economizer in the liquid phase at a certain pressure from state 4 to state 5 till it becomes saturated liquid. In the evaporator or the boiler proper, there is a phase change or boiling with the state changing from 5 to 6 by absorbing the latent heat of vaporization at that pressure. The saturated vapor at state 6 is further heated at the constant pressure, which leads to the superheater to state 1 in the vapor or in gaseous phase. But for unit mass of fluid, the heat transfer in these three types of exchanges are given by the heat transfer in economizer is H5 minus H4, in evaporator it is H6 minus H5, and in the superheater it is H1 minus H6. So you can see here the superheater, the evaporator and the economizer. The states I have mentioned already over here. You can see the 5, 6, 1 and all. These are the states. So these are the different cycles. This is actually the PV diagram, the TS diagram and the HS diagram. You can see I have also mentioned the states over there. So this is the fraction of total heat transfer. So you can see this is actually the heat transferred in economizer, evaporator, and this is in the superheater. And this is the supercritical boiler pressure. So you can see from the liquid the critical point how it actually goes. 1 to 2s, 3 to 4s and 4s to 1. So let's move on to Carnot cycle. The Carnot cycle is an ideal cycle but non-practical cycle which gives the maximal possible thermal efficiency for a cycle. For a Carnot cycle, that is from 1, 2, 3, 4, I will show in the TS diagram. It compresses of a very wet steam at state 3 which would require a compressor of size and cost comparable with the turbine. It would absorb work comparable to that developed by the turbine and its life would be short because of the blade corrosion and cavitation problems. For the cycle 1, 2, 5, 6, 1, the pump work, that is H6 minus H5, is again very high and it is impossible to supply heat at infinite pressures and at constant temperature from state 6 to state 4. So the Carnot cycle cannot be realized in practice. So this is the TS diagram of a Carnot cycle. So I can see here the states 1, 4, 6, 5, 3 and 2. Let's move on to the mean temperature of heat addition. In the Rankine cycle, heat is actually added reversibly at constant pressure but at infinite temperatures. If Tm1 is the mean temperature of heat addition, then the area under the states 4 and 1 is equal to the area under the states 5 and 6. So it happens under the ambient conditions. So only during the ambient conditions you can actually see the mean temperature of heat addition. And it follows a phenomenon, the higher the mean temperature of heat addition, the higher will be the cycle efficiency. So you can see here the TS diagram of a mean temperature of heat addition. This is the formula. So Q1 and the Tm1, which is the mean temperature of heat addition. And by this you can actually get the Rankine efficiency, which is actually F into T, mean temperature of the heat addition. So what is the effect of superheat in the mean temperature of heat addition? The effect of increasing the initial temperature at constant pressure of cycle efficiency will be shown in the next slide, that is the TS diagram. When the initial state changes to 1 to 1 dash, the Tm1 or the mean temperature between the 1 to 1 dash is higher than the Tm1 between the 4 and 1. So an increase in superheat at constant pressure increases the mean temperature of heat addition, hence the cycle efficiency. Moreover, with increase in superheat, the expansion line of steam in the turbine shifts to right, and as a result of which the quality of steam at the turbine increases and the performance of the turbine improves when the effect of superheat is there. But the disadvantages of superheat mainly are it reduces the thermal irreversibility as well as reduces the cycle efficiency. That is, when the overall temperature difference, it results in reducing than increasing the cycle efficiency. So as told, the effect of superheat on the mean temperature, you can see here, this is the PV diagram for that, and the superheat with hot pressurized water as in the pressure working reactor. Moving on to the effect of inlet pressure, the maximum temperature of steam that can be used is fixed from metallurgical considerations, that is, the materials used for manufacture of components which are subjected to high pressure and high temperature steam like the superheaters, valves, etc. This is called the metallurgical limit. So what are the effects of inlet pressure? It actually increases the operating steam pressure at which the heat is added to the boiler. And then it also helps in increasing of the turbine inlet pressure, that is the ideal expansion line of steam. It shifts to the left and the moisture content in the turbine exhaust increases. If the moisture content in the steam increases, then you can tell it actually decreases the life of the blades. It leads to corrosion. And you can also see that the maximum moisture content should not exceed above 12%. So thank you guys for listening to this. Have a good day.